Good evening and welcome to the Spring 2017 Alan T. and Linda M. Beimfohr Lecture. My name is Carl Johnson. I'm the Executive Director of Chesterton House, the Center for Christian Studies here at Cornell, and an affiliate member of Cornell United Religious Work. The Beimfohr Lecture, which is made possible by Carl and Elaine Noyce and named for their friends Al and Linda Beimfohr, is designed to address issues of faith in a pluralistic society and has been called by Cornell Professor Emeritus Walter Lefebvre one of Cornell's most distinguished campus presentations. We'd like to welcome all those who are tuning in remotely via live stream this evening, and especially the Beimfohr and Noyce families, and we'd also like to thank them for making this event possible. This evening's speaker is a cancer researcher. And before I introduce him, I'd also like to take a moment to recognize another friend of Chesterton House, Anthony Carpet, who succumbed to cancer just 3 days ago. Anthony, a 1990 graduate of the Industrial and Labor Relations School, was a great friend to Cornell University, a great friend to Chesterton House, and also a great friend to our other benefactor, Carl Noyce. Carl and all of us here at Chesterton House extend our heartfelt condolences and also our prayers to Sandy and to their children. Like other Christian study centers at major research universities around the country, Chesterton House is committed to human flourishing in all spheres of society. Toward that end, the Beimfohr Lecture has featured distinguished historians, sociologists, and public intellectuals. And this evening, it is our privilege to host medical researcher, Dr. Jimmy Lin. The mapping of the human genome, one of the great scientific achievements of all time, holds great promise for health and human flourishing. But it also holds great peril. As with earlier medical advances, this new technology raises fundamental questions about what constitutes human flourishing and even what it means to be human. All of which is to say that the practice of science raises ethical questions and issues that science itself cannot answer, but which must be addressed by a multiplicity of traditions of inquiry, including religious traditions. To help us think about these things, about how technology might humanize rather than dehumanize, it is our great privilege to host Dr. Jimmy Lin. Dr. Lin is the Chief Scientific Officer of Oncology at Natera, where he is leading the development of new diagnostic technologies for cancer. He is also a social entrepreneur, serving as the founder and president of the Rare Genomics Institute, the world's first platform to enable any community to leverage cutting-edge biotechnology to advance understanding of any rare disease. He has served in a number of academic posts, including Director of Clinical Genomics at the Genetics branch of the National Institute of Health and the National Cancer Institute. He also serves on a number of boards in both the for-profit and the nonprofit sectors. He was educated at Yale and Johns Hopkins, and though this might not be exactly what some overambitious Cornell students most need to hear, he was at one time working on 4 advanced degrees simultaneously. An MD, a PhD, a Master of Health Sciences, and a Master of Arts and Religion. He has numerous publications in leading journals such as Science and Nature, and has been featured in major media outlets such as the New York Times, Wall Street Journal, Washington Post, BBC, Time, and Wired. Dr. Lin is a 2012 TED Fellow, and his inspiring TED Talk is very well worth watching. Please join me in welcoming Dr. Jimmy Lin.
So before I start, I'd like to get to know you guys a little bit. How many of you are undergrads? Okay, and then who are grad students or above? Okay, who are studying sort of the sciences versus the humanities? Okay, more science-heavy crowd. And then who comes from sort of a Christian tradition, a Christian background, and then a non-Christian background? Okay, good. Okay, so it's a big topic today that we'll discuss, and I'm trying to cover a lot of ground, but we do have a long Q&A session, so we'll take advantage of that. The first disclaimer, all these views are my personal views. Has nothing to do with the company I work at, a nonprofit, or other institutions. So humanity's sort of relationship with technology has been sort of explored for a long time, right? So who knows this is a picture of? Icarus, right? So Daedalus is one of the known sort of Greek innovators. He had many inventions, including creating a wooden bull. I don't know if you sort of know that story. Eventually creating the Minotaur, also creating the labyrinth, resulting him to be locked up on this island by King Minos. And then for him to escape, because of all his creation, he had to create these wings, and the famous story of Icarus flying too close to the sun and falling down. So we're thinking of technologies as ways as benefiting humanity, but also as ways of sort of hubris and potential sort of a dark side of humanity, of technologies. So at the start of the scientific age, there was a lot of optimism of thinking of what technology can do, right? And this is potentially one of the fathers of this new age, Francis Bacon, writing about a new Atlantis, where it's almost like a university, where it's sort of ruled by scientists and discovery and thought, combined with religion, of this sort of a utopian world that was imagined. And this was sort of the optimism at the time, as science was starting to boom and new discoveries were coming. But before long, we started to think about what are the other sort of potentially not so positive things that science can do. And as we go later into sort of 19th century and 20th century, we have examples, for example, like George Orwell, who thinks about the governments using science and screens to watch everybody and having a surveillance state, which some may say we already are watching ourselves today. But in parallel to him, of course, there was Aldous Huxley, who explored not only sort of technology in terms of screens, but in terms of genetic engineering, also conditioning, and pharmaceutical sort of the soma thing that enabled the government to control its population by not only engineering a group of people, but training them to perform certain tasks and giving these sort of drugs to make them sort of complacent. So there were sort of these sort of balances of there's an optimism of how technology can be used for good and ways that it can be abused and potentially used for ill. And this tension has really sort of been as with every new technology. And as we talk about genetics, because we're not only changing our environment, we're thinking about potentially changing the essence of what we are, of who we are, our DNA, that has become very, very controversial. Of course, with the modern stories, storytellers are in movies. And Gattaca is one of the stories that we always have to bring up when we talk about genetics. And in a world of potentially where they're using genetic engineering to create two potential populations, the valids and invalids, who are ones that are created with perfect genetics and ones with not, and sort of starting to explore questions there. And a lot of these would think that, wow, that's science fiction, that's far away. But recent developments in biotechnology has made people to start think, are these things closer than we think? And should we start be worrying about the possibility of genetic engineering and these stories portrayed in movies? So interestingly, the development of modern genetics is rather it's a rather short history, but it's so much part of who we are as a society that we don't remember. So DNA was sort of discovered in terms of helix, a little bit more than just 50 years ago, right? And we only sort of knew about the genome about sort of a little more than 10 years ago. But this explosion of understanding genomics, understanding how to read and write the genome is sort of unprecedented in terms of its technology. So in this talk, I'm going to sort of split up into sort of 4 sections. I'm going to split the first half talking about the science of what are developments, the past, present, future of reading genomes, understanding our genome and what that means. The second half is about editing and writing genomes. So sort of very parallel to how my 4-year-old and 2-year-old sort of learn languages. So first learning to read and then to write. And then the second half, I'll start talking about what's the role of knowledge areas outside of science. Is there a role of faith in these areas? First, making a case that there is a role for faith to be in these discussions. And then at the very end, to sort of provide, using a faith tradition to see how that could be helpful as a rubric as we think about these questions. So first, let's talk about science. And we'll do this rather quickly to sum up a lot of discoveries in a short while, but we'll do this quickly. The first part is reading and decoding genomes. And this is an area where I think people have heard about the Human Genome Project, has probably sort of understand a little bit more. And this is an area where popular media has described it more. Of course, if we want to start talking about reading and understanding genetics, we think about the father of genetics, Mendel himself, who was a man of faith himself, looking at peas and sort of figuring out that there are characters in these peas through mating that can result in very predictable inheritance patterns. But it was not until over about 100 years later by these scientists here, Avery, McLeod, and McCarthy, who proved that there's the substance that's been inherited is the substance of DNA. So there was a question, is it DNA, is it protein, what is the substance of inheritance? So figured out that it was DNA, and only in sort of a few years later, in 1953, this is a famous picture of sort of Watson and Crick. Be able to sort of figure out the structure, that DNA is a double helix, and that has implications, that it has pairing, and that's how we're able to figure out replication. And also, then we're able to sort of start thinking about how we're able to create more copies of it and decode it from that. What's significant is, if I said is, it's 1953. So that's only a few generations ago. And that's only when we knew that DNA was a double helix. I think you ask any kid to think about DNA, it's sort of like, oh, every day. But we only knew this for a little more than 50 years. And one person that often is left out in this, and I always when we talk about sort of genetics, is Rosalind Franklin, who was the great woman scientist, X-ray crystallographer, that took the picture of the DNA that Watson and Crick eventually sort of decoded. And it's always good to sort of recognize her amazing efforts for us to be able to understand the structure and DNA. So after you understand that DNA is sort of base pairs, there's 2 of them. The next step you figure out is how does it code? And this is sort of the next scientist, Nuremberg and Mattei, were able to figure out that DNA is actually a very, very unique code. For those who aren't in the sciences, that DNA has a triplet code. So DNA, there's 4 letters, A, T, C, and G. And they figured out that every 3 letters of DNA codes for 1 protein. Some really elegant experiment to be able to do that. So again, this is only within the last sort of, within 100 years, probably 50 years or so, we even knew that there's some sort of code, the genetic code, be able to do that. And this is Dr. Sanger, double sort of Nobel Prize winner, and he is the father of figuring out how we're able to actually sequence. So he was, for the first time, allowing us to figure out ways to actually figure out, these 3 billion base pairs. What are those sequences? So we didn't know how to even read the letters of DNA until very recently. So this is the 70s, right? So this is how short time it has been that we talk about genomes, but we were like, wait a second, only in the 70s we even knew how to read 1 letter at a time. And this is why often it's the output of these sort of DNA gels. If people are in biochem or maybe you run some of these, be able to sort of figure out different mutations as it's sort of pointed there by running these big gels on ways to end replication of DNA to be able to figure out the sequence. So from then on, from the late 70s, there's a rapid sort of uprise of our ability to start reading genomes there. This became more automated through computers and technologies, and you can see how old this old Mac is. As they're able to start reading this, and this is state of the art. Instead of reading these big gels, we're actually able to use these computers to be able to do that. And ultimately, there was sort of big machines that are able to read DNA sequences very laboriously, but able. And then there was a dream then that we're able to sort of read, tens, hundreds of sequences at the same time. Is what if we're able to read the entire human genome, 3 billion bases? And everybody thought that was a crazy idea. And in the late 90s, and you know what? The thought was, let's set a very, very high bar and enable sort of development of new technologies. So maybe one day we'll be able to reach it. And this is sort of the story of sort of science geekdom in terms of the big fight between a private initiative and a public initiative. Here, Francis Collins leading the public initiative funded by the government, sequencing parts of the genome. And here as well, Craig Venter with a private initiative trying to sequence as much as he could as well, wanting to patent it and profit from it, and a big fight. And at the end, through sort of government intervention and sort of ultimately, it was declared a tie, and they sort of came together through a sort of White House conference, and so that was sort of a historic moment that sort of, even though there was this big competition, they came together and for the first time decoded the human genome. This seems humongous as we think about it, but on one hand, it's a humongous feat for us to be able to understand all 3 billion base pairs. But on the other hand, that was only one genome. That was the first genome. So imagine if you're first learning how to read, right? So you first learn there's words, you think there are letters, and this is the first time you're reading your first book, right? And it's maybe for a small kid, that's a big accomplishment, but us as adults looking at it, they're just reading one book. But this was the first book that we're able to read. The thing is, we're able to read the letters, like my 4-year-old son's often sort of be able to read and sound things out, but we don't understand what the genome means. Out of the 3 billion base pairs, approximately 3% of it codes for some sort of information that we can recognize. And out of that 3%, people vary between 30 and 50%. We actually know what that means. So we mapped genomes for the first time, and now there's a big task of understanding what it means. And after the Human Genome Project, now there was a sort of an explosion of new technologies to understand how to sequence genomes even faster. And these are 2 example technologies called next generation sequencing technologies that instead of reading genomes one at a time, it's considered massively parallel. So all of a sudden, it didn't take us decades to read genomes. It became years, and now ultimately weeks. And now we can read genomes in days. And genome sequencing centers are now, sequencing machines are now potentially as small as a USB drive. This actually is an actual product that is able to sort of sequence genomes even today. And they're getting even smaller to be able to do that. So our ability to read genomes and digitize genomes has been sort of dramatically increasing. And a chart that often people draw here is the blue line here is Moore's Law. That's how computers are advancing, sort of the doubling time of about a year and a half. And the orange line is how quickly the cost of sequencing, and you can see it blows away computer technologies. So our ability to sequence genomes, a drop of price versus a drop of computer price, you can see the big difference. So what took, at the beginning of sort of 2000s with the Human Genome Project, one genome cost approximately $3 billion. Or if you want to call it, billions of dollars, and we can now do it in thousands of dollars. So it's a million-fold decrease. So that's a huge, huge accomplishment in very, very short order. And the numbers of human genome sequence, you can see it took a long time to get the first one, and now we're doing tens of thousands, and now hundreds of thousands to be able to do that now. But the thing is, we can sequence a lot of genomes, but we're only starting to figure out what it means. So these are some disease genes. WES is whole exome sequencing and whole genome sequencing. And if you can look at actually the y-axis, so sorry for non-scientists or people who don't like graphs, but you see, we're only at sort of about 220. This is only, so we only know about a few hundred genes in terms of disease. There's 20,000 human genes that we know about. So we know only very, very fraction amount of what it actually means. But the press has already sort of taken this and sort of made this sort of bigger statements. That's sort of often the role of the press. And sort of showing, here, for example, here at Time Magazine, that, once you can, sequence the genome, you can tell, whether this kid will get cystic fibrosis or cancer or Tay-Sachs. Some of those are actually true. Some of those are very well-known genes, but some of them we're still in terms of figuring out what that is. And then ultimately, there's this area where, depending on your genetic background, you can have special drugs that you take for that. That's partially true, but that's actually very few targeted drugs, mostly in the cancer, that you can do that. But there's a big promise now, because we're so good at sequencing genomes, we can sort of know what your genetic future is. We can now sort of figure out, what you're going to be best at, what food is best for you, what diseases you'll get, and that's sort of the dream that often people are sort of talking about. And this is not even for adults who are born. So in 2012, one study that was published in Science Translational Medicine actually took blood in a pregnant woman and was able to sequence the entire genome of the baby in the womb by just taking blood. So we can even determine the whole genomic sequence of a baby that's not even born yet. Again, we don't know what it means, but we can assemble that code to be able to do that. And cancers these days, and this is area of my work, is we're sequencing large gene panels or sometimes exomes on a very regular basis now, because there are specific cancer drugs that are used for specific targeted therapies, and now new immunotherapies are requiring us understanding the mutational rates there. So in the area of cancer, genome sequencing actually is starting to become the standard of care. But like I said, we're only at the beginning of the race. This is the beginning of the marathon. Like a little child, we just learned the language. We just learned that there's letters. We just read the first book. We're just starting to read. We don't know what it means. And there's sort of a large amount of learning that's ahead of us in this marathon. Some of the work that is starting to sort of understand what these areas, this is one of sort of my mentors when I was at Yale, Mark Gerstein. Some of our earlier work studying the first genomes that were sequenced, but one of the initiatives that he's leading now is what's called the ENCODE project, the encyclopedia of elements there of DNA. So out of the genome, about 3% of them we know some sort of what it means, but 97% we have no idea. So there's large international efforts to try to figure out what does that rest of the 97% mean to be able to do that. This is another my mentor, from my PhD mentor, Bert Vogelstein, the father of cancer genetics. With him, we worked on mapping the first cancer genomes. We did it in colorectal and breast cancer, and glioblastoma and pancreatic cancer. It took us 2 to 3 years to map about a dozen, and now in our labs we do that, in an afternoon. But from those earlier work, in terms of understanding cancer genomes, there are again large international initiatives now. Different countries are sort of split up, divide and conquer all the different cancer genomes to be able to understand the context. And then the big dream is the sort of dream of big data, which some people believe, some people think is a myth, but if we sequence enough genomes, then we'll be able to sort of figure out what it all means, and we'll be able to take someone's genome and be able to sort of make sense of it just by the sequence. And some of you may have heard that there's additional government initiatives, whether it's former President Obama with the Precision Medicine Initiative, or Vice President Biden with the Cancer Moonshot. So there's efforts to be wanting to do that. And why is it that these efforts are in existence? Is that the thought that the more of this data set, the more books that we read, right, from different types of people, we know that what they mean, and to do compare and contrast, then we can understand what the different sections mean, and make better sense of it. And that's why there's these initiatives to gather lots and lots of data, not just in the U.S. For example, the United Kingdom has a 100,000 genome project that's ongoing, and countries all over the world are entering in this effort. So before I go there, is that while we are able to now read genomes in a very, very cheap and fast manner, people are talking about a $100 genome or even $10 or free genomes, the caveat is that as scientists, we still don't know what the genomes mean. So this is what we want to sort of think about is as there's sort of hype on this sort of thought of genetic determinism, that we're going to read your genome, we're going to know what's going to happen to you. That is still mostly not a reality within science. The understanding of the genome is still very sort of rudimentary and sort of starting in its phase, and that's very important as we talk about these discussions, that we sort of don't sort of overhype these technologies. So we know how to read. How about writing? Can we write genomes? Can we create genomes? And let me walk you quickly through the history here. And this is Alexander Todd. He is one of the first to actually synthesize and be able to create little bits of DNA in little chains to be able to do that. And this was done around that time, the early 1950s. The first writing, this is Dr. Ham Smith and Dan Nathans. I actually studied with Dr. Nathan's son. They created the first scissors to be able to cut little pieces of DNA based on sequence. So then we can start manipulating them. And that this is one of the first DNA synthesizers to create little bits of DNA, to be able to print DNA, very, very little small pieces. And what was a big, big discovery then is this is Kerry Mullis in sort of the 1980s, actually a little bit earlier than that, had this amazing sort of discovery with using a special enzyme from a very extreme thermophile to be able to copy lots of pieces of DNA so we can manipulate them. So we're gathering some of the tools. We can cut pieces of DNA, we can copy pieces of DNA, we can synthesize it, and this is starting to give us a toolkit of potentially manipulating, writing DNA ourselves. This method is called PCR. And scientists have started to use this. This is one example here where the scientist was able to use an E. coli to create artificial circuits, like on and off switches within E. coli. And a lot of this is now used in industrial, in an industry where they're creating biofuels and really not even using as an organism, but using it as sort of mini bioreactors. And that's being used in yeast and E. coli. We're starting to be able to manipulate species in a very, very facile manner. In yeast, almost, there's projects already to knock out every single gene. And basically, we can sort of manipulate in these simple organisms basically as easy as sort of typing on a computer now to be able to sort of create that. So these are people we've seen before. Craig Venter, one of the sequence processing, Ham Smith, doing restriction enzymes cutting, have come together and thinking about what do we synthesize life from scratch. And that's what they did. So they took a microbial species and they printed and stitched together a genome basically from scratch and booted it up in another cell. So it was completely sort of from synthesized from scratch. What's the catch there is the information was already there. They're sort of photocopying from scratch. They took a known sequence and then they're putting it in an already sort of existing cell. But this is sort of giving us a glimpse for us to be able to sort of print life almost from scratch. Of course, that with caveat, but sort of putting in a cell that already has a capability of life. This is Jeff Buca. Also one of my teachers to study with at Yale, and he actually pitched this project to me as part of my rotation. He's like, Jimmy, why don't we synthesize the yeast genome as a project? I'm like, I don't think I can do that before I graduate. And just 2 years ago, he finished one chromosome. I'm like, man, I'm so glad I didn't take that project for my thesis. So what he did was he made it into a class and had students I'll take little bits of it. And in 2014, they announced that he was able to synthesize one yeast chromosome to be able to do that. And I asked him, I remember when he sort of pitched me, so what's the effective? But it's cool. I'm like, do you want to like make new beer with it? Do you want I think there's sort of, but I think sort of proof of principle that we can sort of create chromosomes from scratch to be able to do that. And now there's companies that's sort of 3D printing DNA faster and faster. This is one of the companies using the laser called Cambridge Genomics, and they can print DNA. You just send them a file of what you want to be printed, and they can send it back to you. Of course, there's special measures to make sure you're not a terrorist printing horrible things, but you can almost sort of do this from your home to be able to start print DNA. So this is the price of printing short oligos, and you can start see it. It's starting to drop from tens to down to 0.1, and before long it'll be again to print DNA. You can just sort of take out your credit card. It'll be like tens or hundreds of dollars. You can print out sort of entire species one day to be able to do that. And we can not only print what's existing, this group here, not only, if you remember the genetic code, where sort of the 3 things code for one protein, and there's 4 types of nucleotides, this group, this is just actually announced a month ago, created whole new nucleotides. In terms of ATCG, they created X and Y, and is able to use that in an organism. So we're not only creating what we know about life, now we're creating new language, new letters to be able to do that. And you can now just imagine the possibility for good or for bad of being able to do that. And this is George Church, a very important person in the DNA, Human Genome Project, and all these sort of new technologies is very fundamental there. But the big project now, amongst other things, is they want to start, instead of the Human Genome Project reading, they want to do Human Genome Project writing. So this is actually a few of my friends working on this project, as well as Andrew Hessel here working with Autodesk. They had this sort of meeting to be able to do that, and journalist was invited, and I ended up not going myself, but then somehow someone at the New York Times found out about it, and it became this like, whoa, scientists are meeting in this secret location to wanting to write genome, and it became viral. Like, it was never meant to that, but that actually got that project a lot of press, so it's actually doing very, very well now. So they now have this big plan of being able to print a human genome from scratch to be able to do that. And we don't know how long it's going to take, but this is now what's possible. And we can think about in the future, a possibility, not in the near future, where you can sit on your computer, sort of type away, and this is what people are afraid of, right? You can, choose your traits, choose, hair color, intelligence, and then basically 3D print a baby. And then put in your room, right? That's what sort of people sort of think about. We're far away from that because we don't even know, right? We don't even understand the language yet, but we can actually print up letters to be able to do that. But when people talk about that, that's the thing of more still science fiction. One quick thing we sort of talk about is not only sort of printing from scratch, but also editing parts of the genome. This is Sir Klug, who was one of the first to find zinc fingers, were sort of special shapes to be able to edit genomes that's sort of derived from this frog species. And we've been able to sort of change a little bits of genomes, even in humans and other species, in a pretty sort of effective manner, but it's very clumsy. Every time you cut a new type of DNA, you need to create a new tool. So there's this new technology that's often even talked about in the press called CRISPR. Have people heard about CRISPR? Some have, right? So this is the latest technology. Why is it so exciting? It's that you're able to edit the genome with basically, it has software that you can basically put into it. So instead of creating a new scissor for every time a shape you cut, you can give it a program, and it can cut in different ways. And the software is actually just an RNA sequence. And this is a very, very versatile tool, and now is able to, is of great excitement, because basically we can now very easily edit genomes, and this is so easy that people in garages, in your home, can order kits and be able to do this. This is two of the inventors, initial inventor, Jennifer Doudna, also one of my teachers, as well as Emmanuel Champagnier. They sort of started this technology, found it in bacterial species, and then George as well, and Fen Zhang, who sort of did it in humans, showing that this is possible in mammalian species and humans, and this is the big rush now to sort of figure out how we're able to use this technology, which is originally actually an immune system of bacteria be able to eat special sequences to be able to edit this. Of course, the press is now worked up to frenzy and like, wow, now we can edit. Now can we just sort of choose a baby on your iPad and then sort of send it off to print, and then using IVF, then put it in your womb, and boom, you have the baby that you want. We are far away from that. And these are some covers, right? We can editing humanity. We can now engineer the human race, the gene machine. So all these covers. And here, Eugenics is back, CRISPR, and then this is no hunger, no pollution, no disease, the end of life as we know it. So of course, this is sort of press sort of making big, but what it is that we are at the beginning of not only printing DNA as much as we want, but also editing. First, if you remember from the first part, we don't know what it means yet, so we don't understand the language. But if we did understand the language, we can able to do that. The technology still needs to be perfected. It has off-target effects, so it doesn't only sort of edit the one area. It might edit other areas. It might cause cancer if it is the area. So it needs to be perfected, but it will be. And then the thought is then, what are we going to do with this technology? So already, because this is so easy to do now, scientists all over the world can literally order a kit and sort of try it at home. Anybody with a little bit sort of biochemistry background, molecular biology, can almost sort of literally try this at home. And this is, and there's a big international backlash and thinking about, no, we should not start editing humans. But this is one group in China that just decided to do it. They try to edit this, and basically their paper published in this obscure journal that nobody read, but it caused big news. But they did this was that they are able to edit, but none of the fetuses actually survived. So it's like, oh, the paper was like, oh, we tried it, but it's very hard. I'm like, okay. But that being big news because they're trying something that potentially is very taboo. So because of this, now scientists are very worried, right? So we're able to, number one, read genomes at a very quick and easy way. Now we're able to print, potentially, genomes and edit genomes in a very quick and easy way. What does this mean? What are sort of ethical implications, societal implications, legal implications? Quickly after that event happened in China and the sort of big press, the different national academies got together. The National Academy of the US, of China, people from Europe gathered together in Washington, D.C. and had this sort of international summit to talk about gene editing. And this is where we're starting to sort of shift over to think about where faith sort of plays a role, is that ultimately when the scientists get together, they can talk science. They can say how we do it, how we can do it better, but ultimately science didn't have the tools to tell them whether they should do it, right? Just because they could do it, there was no science experiment that they could do that could tell them whether they should or should not, for example, edit human genomes or not. So they started to bring in, outside experts, about ethicists, people from other countries to sort of weigh in into this discussion. They wanted to invite more sort of advocates from the disability community, which not, but just minorities to sort of enter in this conversation. Because there's a lot of questions that the scientists realized that, yes, we're very good at inventing tools, but when we think about how we're going to use it, we're sort of at the end of ability of science to be able to do that. And this is where we think that the role of faith and ethics has great to contribute. So the first part, sort of to summarize it, is that there is great promise, there's great development even within the last 50 years in terms of reading and writing genomes, and we're just at the beginning. And before we know it, actually, a lot of these things that we think about will actually be reality. So now is the time for us to start thinking about not only the scientific questions of method and technology, but thinking about ethics and morality. And this will start talking about in my second half here. So morality. Science has even within the US, when we talk about things like eugenics, we think it's such a taboo topic. And we forget in terms of even within US history, eugenics actually was something that was discussed actually even prior to Nazi Germany talking about eugenics. And talk boldly in state fairs. This is one state fair in Kansas where they were able to choose. In state fairs you choose, what's the biggest tomato, what's the biggest, the most beautiful cow. This is the fittest family here. You see here, fittest family. And promoting that the fittest family should be, just as you want to grow better crops, you should grow better families. And families who potentially are unfit, who are causing a burden to society, they either shouldn't reproduce, some were banned, or sterilized. And this was, now we think about it, sort of hear about it, we think it's horrent, it's crazy. But in the US, at that time, this was, talked by proper, high society. People were discussing this as a way of sort of helping the society in terms of the human race as a whole. Even minorities. I'm thinking about ways that African Americans, if they can only take the elite of African Americans, they can help African Americans as a race too be able to rise to the top. So as we think that eugenics is such a horrible thing that we talk about, it was actually not long ago a topic of sort of conversation that was not taboo. And when we talk about science and bioethics, there's sort of two sort of examples that people always bring up where it shows that science are unable to answer those questions and resulted in abuses. This is one of very famous from of course, Nazi Germany. And this is a horrible one where you don't see this as well, is they took kids and gave them different diseases and studied them, and then basically then sort of sacrificed them, dissected them to study how these diseases went, right? Scientifically, if people are no different than animals and rats, we do that in rats all the time. If people are no different, for potentially these scientists, there was nothing wrong from a purely scientific perspective, right? But the backlash, from the ethics community, and this is one of the big things from this and others, is that, when we talk about when you do scientific experiments these days on humans, there's an institutional review board, and all these things actually were created because of things like Nazi Germany experiments. And he's like, wow, that's horrible. Nazis are horrible, and maybe the eugenics was so long ago, and maybe there's other countries. But actually in the US, as recent as in the 70s, there was very, very significant abuses. For those who haven't heard this is the Tuskegee experiment, where African Americans were exposed to syphilis, and in the guise of, and at that time syphilis already had a drug, right? Penicillin was able to sort of kill it, to be able to cure, but in the guise of providing free health care to these poor African American community in Tuskegee, they sort of, come in and we'll sort of do your regular checkup, but in fact they were not giving them any medication, and just sort of watching them, the disease progress. And the study was to see the progression of syphilis in the population. And there was ways that scientists sort of said that, this will help the population as a whole because, they're sacrificing, and we learn about it when we can do that. So there's ways that they rationalize that. And for us, again, think that this is abhorrent. And this is as recent as the 70s to be able to do that. So we can see clearly that science alone is insufficient to provide an understanding of what's right, what's wrong, and things that we today think is sort of everyday and second nature, actually even very recently was practiced in that way. So this really underlines, in addition to science, there must be ways that we should think about ethics, think about morality, think about right and wrong to add to this conversation. So what is the role there for these things? A lot of these discussions then, often even for people of faith, they enter this discussion that yes, there needs to be some sort of morality imported. or put in to sort of help us think about right and wrong. And there's sort of, from Christians, there's a couple of different perspectives. One perspective is appealing to natural law. So Christians often, from one faith tradition, they'll appeal to things that, even though that they come from a specific faith tradition, say that, you know what, we should do this because it's good for society, using sort of non-Christian sort of arguments to be able to do that. And that's mostly because to allow for conversation within the public square, to not sort of take sort of a Christian background into these discussions because the other side doesn't have that language. But the other approach is, as more and more, it's interesting as in sort of these ethics dialogue, people are bringing in their perspectives while celebrating their identity. So whether it's minorities who come in and says, you know what, from an African American perspective, this is what I think. From a LGBT perspective, there's sort of even areas called queer bioethics, where people say, you know, as you know, people of a certain sexual identity, I feel this, or people from the disabled community, people do that. So my proposal is that for people of faith, that this is something that we can bring to the table as well. As not necessarily as every time we come to this table when we talk about bioethics, only appealing to things that could sort of be specific in the entire population, but be open and honest about our own sort of faith traditions, and use that as a ways of sort of building arguments of why we think, you know, we should do a couple things. So that's what I'm hopefully to sort of be able to help you think about in terms of as another method of bringing even Christian wisdom to the table, and not to be sort of apologetic about, oh, this is my, because I think what we're really seeing is a welcoming of different perspectives. And in the past, where sort of Christian voices were much louder, there was sort of a silencing of that voice, but now I think that there could be a resurgence of that. So what can that look like? I'll quickly sort of go over some of that. Beginning of life issues, this is talked about to death, so I'm going to skip this quickly, and if you want to talk about more, and this obviously is very, very controversial but there's very sort of clear scriptures in the Christian scriptures about God knowing children while they're in the womb, and that's why I sort of talk about sort of beginning of life issues and abortion, but there's much, much more. And often when we talk about the interaction of Christianity with bioethics, we often sort of stop here, get stuck, or at the end of life. So I like to sort of go into the other issues there. So what are areas of sort of the rich Christian tradition that we can sort of appeal to think about how we think about genomics and science? One thing we think about is the creation mandate. So for people who don't come from the Christian tradition, this is when God created Adam, one of the first things God sort of told Adam was for him to sort of take care of the garden and be a caretaker, and even name the animals to be able to do that. So from a Christian tradition, the pursuit of science is something that actually God mandated, that we shouldn't be afraid of doing science. This is one of the ways for Christians to understand that the world they're in, and understand the God that they serve, but also caretaking. So, you know, looking at different species and be able to do that is very, very important. Imago Dei. Jargon, but this is image of God, and this is a central, very, very important idea within the Christian tradition, that humans are created in the image of God. Humans are different from animals, and because they're created in the image of God, they can understand God's thoughts, and they have human dignity, and this is central now when we talk about this discussion about genomics and human dignity there. So for example, when we talk about humanity, people are different within the Christian tradition than animals. So from a purely atheistic perspective, it's depending on sort of who you talk to, you know, sometimes there's very little distinction between why we should experiment on humans, not on humans, but why we should on animals. Some have actually suggested we shouldn't even experiment on animals altogether. So that's sort of one way of thinking about it. But I think from a Christian perspective, right, again, from a multi-perspective approach, knowing that humans are different from other species, in that sense, we would think about as we approach bioethics, when we're editing genomes and reading genomes and making changes, that we differentiate how we treat, you know, cloning Dolly the sheep versus calling Molly my aunt. So it's going to be very different as we sort of think about people versus animals. Human dignity is very, very important, right? As all people are created in the image of God, in terms of how you approach ethics, we're sort of from Christian ethics, let's think about sort of purely utilitarian. People are only worthwhile if they're producing good to society. So a child that's born, for example, with severe disability or live a short amount of life or not, quote, producing good for the world, they still have dignity. So from a Christian perspective, looking at people who are disabled, who have significant diseases, they too have dignity in that sense. And often from the disabled community, when they sort of voice their opinions, they're saying, it's not often so clear cut what things are purely diseases and what are sort of spectrum of that. But the importance of thinking about what human dignity is and looking at what is disease and what is sort of healthy state is important there as well. Another idea is Shalom and Fall. So Shalom is a sort of Judeo-Christian concept of wholeness, of wellness. And this wholeness and wellness doesn't exist because of we live in a world that there is no wholeness because of sin entering into the world from Christian perspective. How does this then help us think about in genomics? There's a big discussion within genomics is what can we do in terms of the actual changes? There's a big differentiation between editing genomes to help alleviate diseases versus creating quote-unquote superhumans. So if people have cystic fibrosis, Christian, non-Christian alike, within scientists, there's consensus that working on that, helping that sort of makes sense. And it's much more controversial where we're editing genes, for example, to make people higher IQ or bigger muscle. And that also is within sort of Christian, within scientific discussion. But I think from a Christian perspective, we can very from that perspective, be able to say that we are restoring a broken state, and what we use genomics for in terms of that sort of makes sense in that rubric. I sort of talk about restoration there, and ultimately, I think when we talk about new technologies, there's sort of an envisioning of one day where there's sort of no diseases and everybody will be healthy, live forever, land of plenty. And what can that look like in different ways? And I think I like sort of the Pixar movie with WALL-E. People have seen that where they have nothing to worry about. They sort of sit in their motorized vehicles and just sort of sip drinks and watch TV all day. As sort of that idea of sort of utopia. So even one day we're able to edit genes. Let's say we're able to understand genes and edit and be able to get rid of disease. Is that ultimately sort of the answer of what that looks like? From the Christian tradition, there's a thought where there's a time where there are no diseases, and then when people are with God, and that's sort of the ultimate state beyond just sort of a physical amelioration there. So that's something to think about is if biomedicine and biotechnology ultimately is just to restore the sort of physical state of health, of sort of longevity and life, is that sufficient? And I think there's a lot of richness that Christian tradition can bring to. So I'm going to end here. This is a thought. This is a picture of Singularity, where people talk about computers are going to be getting so smart, they're going to sort of run us, and ultimately we're going to just sort of live within machines to be able to do that. And there's a lot of sort of thought about what future will look like. And I think there's, whether with technology or not with technology, thinking about what we want our society to become, what we want humanity to be, and what it is to be human are incredibly important questions that we should ask and compare different worldviews and different traditions and how they're able to answer that question. Thank you very much.
Thank you very much. That was a wonderful and wide-ranging lecture. And you may have noticed that all of our speaker's notes were over here, and he never looked at them, which is very impressive for those of us who are much more dependent on notes than he was this evening. We have some time for Q&A, and let's make the most of it. So let's take what time we have. to ask what questions you might have for our speaker. Just speak up.
Thanks for the interesting lecture. I was wondering, from a practical perspective, even when we have as a society decided, or at least a country decided what the ethical standards are, how will we be able to practically implement it, given that there's always so many other countries, that there's different standards, not even countries, but there might also be private institutions who are doing things that we know nothing about. But especially given the fact that you've mentioned multiple times, that it's becoming easier and easier to do these things. You don't need the big research labs that we can kind of control. So even if we decide on what is good and what is not, how will we be able to make sure that nobody's going behind their backs and doing something else?
Yeah, no, that's a great question. At this conference on the summit, looking at ways to sort of look at genetic engineering, they invited people from different countries, from Africa and France, and to be able to sort of think about how different countries have different standards, and potentially we can think about ways that that there can be some sort of consensus. And let me talk about the consensus first, and then let's talk about sort of the biohackers, which may be the fun part. The consensus is always hard to come, and there are global organizations that are able to sort of do that. So within the area of bioethics, for example, whether with the United Nations or UNESCO, there has been consensus, for example, on human dignity. That even though that different countries may have different perspectives, they have come to sort of a common denominator in terms of recognizing that despite all the different countries of the world, as humans, these are things that we sort of think about what human dignity means. And there's similar things that have happened in different areas, such as sort of human cloning and others. That being said, so cloning is a great example where the scientific community has most countries have said, that's not a good thing to do, an unethical thing to do. But purportedly, there actually are companies who are doing it in secret, and people are saying, there are news reports that there have been people that have been quote unquote cloned. So that's sort of an issue that has been. So I think that in terms of how you're able to regulate ethics is always something that's hard, right? So for example, we say that people shouldn't kill, but there's a large number of murders that happen. So I think there's sort of two questions to say. Number one is sort of figure out as a society or as humanity what we sort of think is right and wrong, and that's number one. And number two, then, is how we're able to sort of implement that. When it becomes very, very easy in terms of sort of biohackers, it is possible actually. To think about people in garages 3D printing like smallpox viruses in the future. And there have been discussions and actually been interviewed by the press about sort of these things. It's not possible these days, but it could be. So what we need to do then is sort of have things that we will be able to attack that. So I don't think we will be able to contain it, because it becomes so easy. In the same thing that people talk about 3D printing guns, and that's sort of now possible. That we need to sort of create mechanisms to be able to sort of go against that, and sort of becoming this sort of ultimately sort of policing and cat and mouse game that happens. So there's not going to be a clear answer because it becomes so easy, but it will require sort of enforcement efforts to sort of keep that at bay. But it is a valid concern, and governments are thinking about that very seriously in terms of bioterrorism, and for us to, so let me talk, for example, about smallpox, right? If we really have eliminated smallpox, and it doesn't, or other sort of diseases where, we no longer vaccinate, but having then actually the therapies and the vaccinations on board in case of an outbreak to be able to sort of mitigate that would be sort of measures that are going to be important to be able to do that. So. Unfortunately, there's not an easy answer that says that there's ways to completely shut them down. You won't be able to. And the ways that to be able to is to survey and be able to respond.
If I could just ask a quick follow-up to that, do you observe any sort of a pattern along the lines of when a new technology emerges and questions or controversies about its appropriate use arise, is there a tendency for the ethical responses to those controversies to move toward consensus over time? it never feels that we have consensus, but partly because there's always new emerging technologies that are raising new kinds of questions.
Yeah.
I think in the beginning with the introduction of a new technology, and for example, cars, for example, right? There was a great concern that on all these people, like, hitting pedestrians, and at one time cars you needed a person to be in front of your car to drive it, and
even bicycles,
yeah,
similar concerns.
yeah. So I think with all new technologies, I think in the beginning we really don't know what its impacts will be. And there's going to be some exaggeration of concern. And then there's parts of it there's going to be legitimate concerns, right? Like if you talk about cars, now we have safer cars, and we have seatbelts, and we have rules of the road. So I think society adapts to new technologies, but they're still going to be adapting in ways that there's going to be ways of restriction and ways of freedom. So cars example, right? They're now, not anybody can drive a car. You need to take a test to drive a car. You need to, not any car can be on the road. You need seatbelts, and you need lights. So there's going to be regulation that sort of help guide that technology. So for example, cloning was a big deal back in the day, and we cloned a lot of things these days, but sort of just not humans. So with new technology, there's going to be guide rails that are eventually established. When it's new, everybody thinks that it's sort of free for all, but ultimately, I think there's going to be more nuance in terms of how we use these technologies.
In the back of the front section there.
Yeah, so my question is kind of more of a Christian position. I'm kind of curious as to exactly what studying or codifying the human genome really will achieve. I know that when you want to stimulate antibodies in your system, when you're fighting off cold or whatever, they mix chemicals and they do some sort of test, and they mix them, and they have an animal, like a mouse, they inject them with this new chemical, and they observe them over time and watch them transform. Has there been any actual success stories of cloning someone? When you clone a new sheep, for example, it's a brand new sheep. It's a completely different sheep. Maybe it has the same DNA or whatever the purpose is. But the only way you can tell if something has been successful is by using statistics. So I know there has been in the political spectrum people trying to classify certain human beings as being smarter than others. A smaller brain may correlate with lower test scores, or a larger brain with higher test scores. And in every single category, whether it be test scores or violence, African Americans tend to fall on the bottom, the ones that get the end of the stick that is the most complex. So how can you make a case? Are you going to try to make a scientific argument and suggest that it has been, you are going to try to find this actual gene, tabulate the DNA and say this gene is the one that you want to stay away from, that will prevent African Americans from killing each other so often, and prevent them or help them or aid them to grow their brain much larger? What is the essence of this science, when as Christians what we try to achieve is suggest that everyone is an individual human being, and God's love will help us attain the greatest heights that we can actually reach?
No, that's a great question. So the question is, why do we study the genome? Are we studying the genome so we can figure out how to make people smarter or better categorize people, or what's the purpose? There's a couple things. Before I sort of even talk about sickness and disease, I think there's intrinsic value in studying God's world as a Christian. So it doesn't have to eventually help even an individual. Someone like a Kepler, looking at sort of planetary motion and marveling at God's handiwork is a way of worship, of studying God and his fingerprint. So there's intrinsic value in studying science in itself, studying God's word. So that's number one. Number two, I think within specifically genomics, I think what I'm actually interested in is sort of restoring the effects of the fall, specifically looking at disease. So I study cancer, and there's very clear genetic signatures that cause that. So understanding the human genome can help us understand which are the disease alleles that cause different illnesses in terms of that. So that I think as Christians, I think, are sort of co-laboring with God as stewards of this world, and sort of working with Christ to be able to sort of turn back the effects of the fall. So that's sort of number 2. Number 3, in terms of the characteristics, that's going to be hard. I think we have, there are some things to sort of tie, for example, traits with muscle growth. So there's specific, that's been found, height as well, to be able to do that. But ultimately, these are descriptive, right? For example, let's say we have imaging technologies like taking X-rays, MRIs, and CAT scan, and we can see that people with bigger hearts or special kind of twitch muscles are better at certain activities. So fast twitch versus slow twitch muscles, more fit to be a marathon runner versus a sprinter. So those are sort of descriptive. So there's also value in that descriptive aspect, but description doesn't mean sort of prejudice and labeling. So that can also, because for example, we can describe people with different skin color, and we can do that as a descriptive manner, or we can do that in a prejudicial manner as well. So I think, so it's a scientific way of doing that, describing that, understanding that has value in itself as well, without sort of falling into sort of categorization and prejudice.
Could you sort of simplify the process by which you guys use to tell exactly how you codify this DNA or double helix? Is it you notice colors and then you say, oh, this color is designated with this? Because I was looking up online gel electrophoresis, and the reason I have such deep quibbles is because as a Christian I find it somewhat perplexing that people are creating science or defining this theoretical aspect of life as if it were truth, as an absolute. It's their new God, it's science, right? You have Dawkins, some social scientists, just continuously railing people, college campuses after campuses. People are creating this new science or this new religion, and then I think to myself, I've studied and YouTubed and Googled, gone to conferences, and nobody can tell you exactly that they can read it as they describe it in a book or they draw it out, or computers can actually apply numbers to certain things. I don't see that. Can you simplify it for me?
Yeah, happy to. So first of all, I think science, there's the interplay between science and faith, and I think as a scientist who's Christian, that science is sort of the way that I worship and glorify God and understand His world. So so science as a tool versus scientism, which sort of seeing science as the ultimate, and that's something separate. Quick primer on how to understand DNA. DNA ultimately is 4 letters, A, T, C, and G. And you can take that, and these machines are able to digitize. So it just becomes a string of letters, A, T, C, G. And simply what you do is, for example, in cancer, you take someone's cancer, and you get the letters A, T, C, G, and you look at their normal, A, T, C, G, and you look at what's different. And those are the positions that are different that may be causing cancer. You take a look at another cancer, and you say, oh, and after a while, you see a pattern. Everybody who gets colorectal cancer, or a large part of them, has a specific gene, has a specific mutation. And that's how you sort of decode. And it's literally strings of letters that scientists are looking at. And it's mostly by comparison. And that's why we sort of talk about big data and wanting to sequence lots of people. Because, for example, we can take a look at all the people with, for example, autism, all the people without autism, and then see the differences in their genomes and be able to sort of map those differences. And it's a comparative aspect.
Yeah, right here.
I had a question about consciousness, but I think first I just want to make a small comment. I think I would be remiss if I didn't. As a neuroscientist and an African American neuroscientist, I think it's important. The study that was mentioned before is something called phrenology, which is an old sort of like quackery type science that had to do with the size of the skull and correlating that to crime or violence, and that's not true at all. And so I just want to say that first and foremost.
Yeah, and actually Jim Watson was sort of highly criticized for saying that as well, which has been completely disproven.
Right, as a neuroscientist, that's complete trash. And as a black person, I'd like to also say it's trash. That aside, I was interested in, as Christians, we talk about being dualist, understanding the brain and the mind separate from the soul. Most of my colleagues are physicalists, right? Meaning that the mind is the brain, and you can, if you can get transistors or something to keep making a brain, you can solve the soul. So I was just curious in terms of sort of the genomic side of things, if you can 3D print life, if you will, where does consciousness fall into that? Do geneticists think about that the same way neuroscientists do in terms of?
Yeah. So there's definitely sort of neuropsychiatric genomics. Actually, some of that is done at Hopkins. It's incredibly complex, as you would understand, is because a lot of, for example, looking at mental health disorders and schizophrenia, there's sort of genetic alleles that predispose people to different sort of mental illnesses, and that's the most. I didn't get to it, that you're more likely that you take all the people with schizophrenia, I think back to you, all the people with schizophrenia, all the people who don't, and these are the people who do have some of the alleles, and you have a little bit more likelihood of being, having schizophrenia if you have these gene SNPs. That's the extent of it. We know, you would know more sort of as a neuroscientist, we know so little about the brain in terms of that sort of complexity. And there's a big step from your genes and how it's expressed to the structures, and then the synapses and neurons that from the genomics perspective, we're still understanding even what the susceptibility alleles are, and that's even a very, very rude first marker. So for genomics to ultimately explain consciousness, that's, I think, very, very far away. And one thing I wanted to talk about is humans and chimpanzees share, I forgot the exact number, but 99.9, I don't know how many nines, percent of our genomes, right? And ultimately, we don't think that, we are humans just because of that little difference between us and chimps. And actually, we share our genome with rats over sort of 90%. So we are much more than our genes, if that's one thing that genomics have sort of taught us, because if we were purely our genes, we're actually not much different from the animals. So there's something more about humans than sort of pure sort of DNA that's sort of becoming clear, and that, if you sort of press scientists on, that they would have to sort of figure out what is that something that's more. And from a Christian tradition, obviously, there are some answers there.
Right here in the front.
I've got two questions connected. You said we understand about 3% of the genome, human genome, and at what rate is that growing? And is that also is that similar to how much we know about kind of the protein world in terms of what we understand or what we have decoded?
Yeah. So the 3% number I sort of use, and I didn't give as much in detail because it was general talk, is approximately 3% of the genome are exons. So the exome is about the 3%. And like you sort of said, those are areas where we know code proteins. And we understand that proteins are what ultimately acts within a cell, then it causes a difference. So because we know the genetic code, we know that every 3 codes for amino acid, and we can make sense of those regions that these exomes code for proteins, and proteins have some sort of function. So those are areas we understand okay. But we don't understand, like a vast number of proteins, we have no idea what it does. And most proteins, we probably know one of many, many functions that it provides. Outside of these areas that encode for proteins, there are, untranslated regions, 3' 5', and we're getting into the weeds. There's microRNA. So these areas, there's a lot of other parts of the genome where it doesn't encode proteins, that scientists are still trying to sort of figure out what it means. And projects like the ENCODE project are trying to sort of figure out, does it contribute? Is it just junk? Is it just molecular fossils? How does that contribute? Why do we, if it doesn't mean anything, why do we have all these areas that potentially are non-functional, or we just don't understand the function?
We'll take 2 more questions here and then over in the back. That'll be the last question.
This question isn't directly pertaining to your research, but what is your opinion on the Biologos initiative?
Yeah, I give entire talks about these topics, and usually the discussion is framed charity, grace, and love at the intersection of science, faith, and evolution. Obviously, there are very contentious discussions and debates and attacks in the area of how we understand evolution and human origin. And there are many different well-meaning, God-believing Christians who stand on many sides of the issue, whether it's young Earth, old Earth, whether it's theistic evolution like biologos, so if I were to sort of summarize these talks I usually give, I think I would, instead of giving an answer, and I don't, by the end of it, sort of tell you this is the one that I think is right, because I don't think that we know which one is completely right, just from the scriptures. It's what is important is to look at three things. You need to understand the science, which is important. You need to understand the scriptures that it refers to, specifically how to interpret those scriptures, which is called hermeneutics. Often people who are in these discussions take passages out of context. So understand how to read the scriptures and how to understand doctrine within the whole book of the Bible, which is often called systematic theology versus sort of biblical theology, is going to be important. So I think the way to address that would be more sort of systematic. You understand what the science is, what's good hermeneutics of those passages in terms of biblical theology and systematic theology, and then that come to sort of your agreement there. So I think ultimately the Westminster Theological Seminary looked into this in the late 90s, specifically about one issue. They're not even looking at evolution, but looking at the word yom as the Hebrew word for day. How long is that day when it talks about the days of creation? And they surveyed historical theology, different fathers of the faith, and how it was used. And basically they said that even before evolution, even before science, people have debated how to interpret that word. And they say that on this side, right now, that there's not sort of a clear answer that you can be sort of dogmatic on how to interpret that. So they, as a seminary, they gave freedom for people how to interpret that. So I think as a Christian, I think we should strive to understand Scripture clearly and come to understanding, but I think we should be charitable and loving to our brothers and sisters who have potentially sort of other views on how that is done, and not to be overly dogmatic, and that in the things that we agree on, probably within these different areas, we agree probably, similar to chimpanzee genomes and human genome, a vast majority, and not to sort of take these areas that, as sort of ways of dividing. That being said, those also has implications too. When you take these ideas and draw, and when they are taken out of context and take science into scientism, or you take methodological naturalism. Sorry, I'm throwing all these weird, long, big terms. But if you just sort of see science and then sort of lift it to its ultimate means, because what you think about evolution, or you think about evolution is true, and that you don't believe in a good God, those also have implications. So it's a nuanced answer where, yes, we want to find a good answer, but we don't want to be dogmatic about it. But there are still ways that can sort of lead brothers and sisters astray, so we need to be charitable to one another when we talk about that. So hopefully that helps.
And last question over here.
Hi. One of the topics that you brought up quite a bit was the difference between right and wrong and how that relates to genomic testing. My question is, how do we justify what is right and wrong in genomic testing, which is still such a gray area, when there are so many different belief systems and cultures across the world? So many people think so many different things are right and wrong.
Yeah, so that's nothing new. So the study of ethics has been along for a long while, and there's many different sort of areas of thought of how you approach ethics. Whether you wanted to look at virtue ethics, or whether it's utilitarian ethics, be pragmatic or deontological, and people sort of disagree on ethical issues and ethical norms. So genomics is no different. So there are many different ethical issues that people disagree on, just like in the area of genomics. But there's ways where there are implications on a societal level that would result not only from ethics becoming legal issues, and then there's areas of ethics that become sort of personal choice within freedom of the law. So there are issues that is up to individual choice. So I think genomics is no different than other ethical issues in that sense, whether it's what kind of food you eat, whether you want to be a vegetarian or you want to eat meat, or what you think about how you do your purchasing, whether in enabling slave trade or fair trade. So there are personal choices, and then there's things that are more societal that would sort of result in sort of legal, sort of governmental sort of regulations. So genomics wouldn't be no different. So there are laws in genomics sort of banning, or it should be the other way, as protecting. There's the GINA Act, Genomic Information Non-Discriminatory Act. So if you get your genome tested, there's ways that needs to be protected. There are, but then within whether you should get tested or not, that's within sort of personal freedom. So I think like all ethical issues, there's going to be a balance there between sort of government regulation versus sort of personal freedom.
Okay, as we wrap up, just a couple of quick announcements. I wanted to mention, as you may have seen on a slide at the beginning, that tomorrow evening, the Chesterton House will be co-sponsoring the Veritas Forum at Cornell. The title of the evening event is Beyond Colorblind, and the speaker is Dr. Andra Gillespie from Emory University. And even before that happens, those of you interested in continuing the conversation with Dr. Lin will be very happy to know that he is on Pacific time. So it's only 6:30 p.m. right now. I plan on taking him over to the Bear's Den. And so any of you who would like to join us, you're very welcome to. Thank you very much for joining us this evening. And with that, please join me in giving a final thanks to Dr.